Let's review some of the things that we learned last time. So one qubit state usually represented as cat notation. And it's a two-dimensional complex vector. And we also talked about n-qubit state. So we also denote the same way we do for one qubit state, but when sometimes if you want to indicate that it's n qubit instead of one qubit, you put n as a lower script, and it's a sum of tensor products. So so what's the index? Well, you could have infinitely many, but not really infinitely many if you have a fixed basis, but it's just a finite sum, let's say. It's just a finite sum of this kind of tensor product. So this one, 0 to n-1 is index, and I use the index from 0 because eventually this index will be the decimal point. So actually binary point, the binary place of the digits for binary representation. We're going to talk about this shortly. So anyway, so these ones, each of these are the one qubit state. And we talked about what is this tensor product last time, and that's basically putting all these vectors together to make a new vector. So the n qubit states is also vector. So we denote Hn and H1 as the vector space of one qubit states and n qubit states. And they're not only just vector space, they have inner product, so it's called Hilbert space, and that's why we put H here. So it's the set of all one qubit state, and this is set of all n qubit state. And now let's talk about how to represent n qubit state and one qubit state in different way, because we always talked about this is a vector, and we know matrix is the best way we can represent a vector or the transformation of vectors. So let's introduce that. So first, let's say we have one qubit state. Then we can also relate or corresponds this one qubit state as 2x1 matrix, alpha, beta. So this is 2x1 matrix of complex entry. Okay. And so you can see that all the vector addition and scalar multiplication on the one qubit states are identical to the vector addition and scalar multiplication of 2x1 matrix like this. And let's talk about the tensor product. So how about n qubit state? How do you represent n qubit state as a matrix? So we need to introduce the tensor product between matrix. So the tensor product between two matrices. Let's say first one is n by m matrix A, and let's call the ij's entry of the matrix A to be aij, and P by Q matrix, let's call it B, and we don't really use the index LK, but let's call the index, the entry of LK entry as BLK. So when you take the tensor product of these two matrices, so it's not a matrix multiplication. Tensor product can be taken for any two matrices. So when you do that, is the NP times MQ matrix, and we denote it as A times B. So the order matters, but you can take any two matrix and take a tensor product such that, so this is how it looked like. So it has NP rows and MQ columns. So I can make a block of sub-blocks of big matrix blocks. And the first block on the top left corner here is A11 times B. So here, I put the entire B matrix on this block. So it's basically not just a number, it's just array, two-dimensional array of number here. And then A1, 1M times B. So here, when I say times B, this times B and this times B, it means that all the entries in this block is not just the same entry on matrix B, it's the multiplication of each entry in B with this constant. And same for here. And here, AN1 times B and ANM times B. We can see that there are NP rows and MQ columns now. So let's see an example here. If I take 1, 0 tensor product with 0, 1, so this is 2 by 1 matrix and this is 2 by 1 matrix. It's going to be 4 by 1 matrix. So how do you make that 4 by 1 matrix? Simply put the right-hand side matrix to the left-hand side by multiplying each entry as a constant. So we have 1 times 0, 1, 0 times 0, 1. So mostly, if we can put anything in the entry of matrix, but here we don't consider it's a matrix of matrix. We just take out all the bracket here and then make it into 4 rows, 0, 1, 0, 0. Okay, so this is how the tensor product between the matrix are defined. And so we can use this tensor product representation. So let's say we have n here. So let's say I have an minus 1, 0, cat, beta an minus 1, 1 cat, tensor product up to alpha 0, 0 cat, beta 0, 1 cat. Then I can identify this n-qubit state as tensor product of n different 2 by 1 matrices. So first one is an minus 1, beta n minus 1, tensor product, alpha 0, beta 0. So how many rows does this tensor product have? So every time you multiply a tensor product matrices, you multiply the rows, number of rows. So it's going to be 2 to the n times 1 matrix. Okay. All right. And this representation is very useful when you compute the actual state with the operations that we're going to introduce maybe next time. And also, it's important to know that there is a matrix representation of bra. So let this be the bra psi be the bra of psi. Then the matrix replication. So actually, you don't have to write this way, so because this already indicates that this is the bra of the cat psi. but I just mentioned that with this way. So it's fairly automatic that whenever you see the bra, there should be a cat, and when you want to represent the bra with the matrix representation of the bra, is the conjugate transpose of the matrix of psi cat. So, as I said, when you take the bra from the cat, sometimes if the cat is the n-qubit state, then you have to reverse the order, and also you take the bra of each 1-qubit state. And when you do that, basically 0 cat is turned into 0 bra, but the coefficients become conjugate of the original constant. So there's that conjugate, the same conjugates is here. And transpose is basically you turn the row and column, switch the row and column. So here's an example. I'm just making a random state here. Let's say we have this quantum state, and what's the matrix representation? So the 2x1 matrix, I and 1/2. And what's the bra of this cat state? So you just take the bra of 0 and 1, but you take the conjugate. The conjugate of I is minus I, and conjugate of real number is the same. So now, what's the matrix representation? It's not 2x1 matrix anymore, because you have to take the conjugate transpose of this 2x1 matrix. So when you do the conjugate transpose, then it's 1/2 matrix minus I 1/2. Okay. So why is this useful? Because this matrix representation, when you use the bra as a matrix representation of bra, you can turn the bracket operation into simple matrix multiplication. So here, bracket. So what is bracket? So let's say bracket operation. What is the bracket operation? It's the inner product. Simply, it's the inner product in Hn is computed by matrix multiplication. So it's very evident from simple multiplication like this one. So let's take a few of them. So we know that the bracket of 0, 0 is 1, 1, 0 is 0, and let's make it into a multiplication between two matrices. So bra of 0 is what? 1, 0. Yes, 1, 0. Right? And because the cat 0 is 1, 0. Right? So when you take the multiplication of 2x1 and 1x2 and 2x1, you can get a 1x1 matrix. 1x1 matrix always considered as constant number. So just put 1 here. And how about this? So we have one bra, which is 0, 1, and cat 0, 1, 0. You can see that it's 0. So you can compute the bracket operation with the bracket notation, but you can always do the matrix multiplication. So it's very useful when you want to implement the quantum state in the classical computer, or you want to carry out the computation mathematically, then you always have to go through the matrix representation. All right, so let's do some exercise. Before we do the exercise, if you have any questions, let me know before we do the exercise. Yes. This one? Yes. See, yes.
The multiplier of the matrix, I'm wondering how it can be expressed like that, because we learned that the half of the 1/0, so it's the upper side,
So it's a
I can understand the
two matrices. Okay. So it's 1 by 2 times 2 by 1. Okay. So basically it's going to be 1 by 1 matrix. And there's only one entry. So you take the first row of the first matrix and the first column of the second matrix. And you multiply entry by entry. So 0 times 1. So let me write here. So 0 times 1 plus 1 times 0. Yes.
사이가 슬래시 사이 중괄호 그다음에 괄호 사이 슬래시 이렇게 돼 있는 것만 배웠는데 이게 어떻게 이렇게 합쳐졌을 때 저렇게 멀티플라이가 될 수 있는지.
Oh, you mean how can I get this when I multiply this? So this is just notation from physics. So physicists developed the notation of inner product between two matrices. So two vectors, two quantum state. And whenever they take the inner product, so basically, so this is inner product between one cat and zero cat. So let's say this is the inner notation of inner product. So whenever you want to take the inner product, the physicists develop the bracket notation. So you have to turn one thing, the left one, as a bra of the cat state. And then it becomes a bra. And then you put them together. And so there's two bars, but they just put in one bars each other. So probably they have different meaning. But as far as I understand, there's no difference in computation with this bracket operation and the matrix multiplication, because the process of computation is basically this process. So you take the two vectors, and then in order to carry out with this notation, the computation, and you take this one as a bra, and then you combine these two bars into one, and then make it a simple notation like this. Yeah. So I asked, so after I learned about this, and then I asked some professor in physics, and I told them that the quantum mechanics, quantum computing, quantum state, I think it's just about vectors and matrices. And he said, no, the physicists have, some kind of but I asked what it is, and I think it's too complicated to state in one word, but I think physicists have deeper understanding of the, state itself, and the symbolic notation of the quantum state is kind of represented in there. So, but I don't know what's the deeper meaning of the quantum state that physicists think about. Any other questions? No? All right, so let's look at some example here. I want you to do the exercise with me. So, so here, let's represent the following quantum state. So whenever I say just state, it means quantum state, because no other state we're talking about. So first one is a cat state. And second is 2-qubit state. And the last one is also a 2-qubit state. Okay, so I'll give you some time to do on your own, and then we can do it together. So first twos are easy. So this one is just 2x1 matrix, and this one is tensor product between 2x1 matrices. And let's look at the third one. If you want to do one or two together, if you want to see how to do the one or two, let me know now before I do the number 3. Anyone want to stuck at 1 or 2? Anyone stuck at 1 or 2? No? So I think it's fairly straightforward if you just follow the definition I mentioned. So let's look at the third one. So so this is a 2-qubit state. It's a linear combination of tensor product between two 1-qubit states, and I split them up with 0, 0, 0, 1, 1, 1, and there's one more actually. It means that there is at the coefficient is 0 for 1, 0. And you can use the matrix addition to represent this ket state. So what is 0, 0 here? So this is represented as 1, 0, tensor product, 1, 0, and then it's 1, 0, 0, 0, right? And then let's look at the tensor product 0, 1. So this is 1, 0, tensor product 0, 1. So this is 0, 1, 0, 0, right? And let's look at 1, 0. This is 0, 1, tensor product 1, 0. So it's 0, 0, 1, 0. And the last one, 1, tensor product 1. It's 0, 1, tensor product 0, 1. Therefore, it's 0, 0, 0, 1. So we know that 2-qubit state, the set of 2-qubit state, is 2 to the power of 2-dimensional vector space, which is 4-dimensional complex vector space. And we have representation of any 2-qubit state as 4x1 matrix. of complex entry. And whenever you want to represent this 4x1 matrix, set of 4x1 matrix as a vector space, these four matrices are the standard basis, right? The straightforward basis. So you see that these states becomes the basis of set of 2-qubit states. And this quantum state has these coefficients with these bases of vector space. So if I want to represent it as a matrix, then just see where the coefficients go. So 0, 0 is the first top here. Only have 1 on the top. So it's going to be 1 over 2 squared root of 3. And how about 0, 1? It's 1 over 2. And there's no 1, 0, so it's going to be 0. And the last one is minus 2 over 3. Okay. So you can see that now that there's some relationship between the tensor product between this base state. So we call this 0 ket and 1 ket as a base state. But as I said, I think one people mentioned about this in the first class, that when you say 0 ket and 1 ket, that's not an absolute state. It's a relative state based on what kind of orthogonal basis you're talking about. But anyway, for now, just think that 0 ket and 1 ket is an absolute measurement basis. And then whenever you fix that, then, so let me put a remark here. Only thing we need to keep track of whenever we talk about this n-qubit state is in what order does this 0 and 1 are product each other through this tensor product. So if I say 0, 0 lined up this way, it doesn't matter whether I put the tensor product in between or not, because it's always tensor product. If you want to make a 2-qubit n-qubit state, you always have to use the tensor product. But so usually people just simply write this way. But this 0 ket and 0 ket is, by nature, it's not the same 0 ket. It's the 0 ket information. It's an information which is stored in some certain material, the quantum material. So we call this is the 1-qubit state stored in qubit 1. So we can name the qubit that has that information. So it's a quantum state it's a quantum state of qubit 1. And how about this one? So it's a quantum state of qubit 0. So the same way we indexed our 1-qubit state in the tensor product of those qubit state in order to make n-qubit state, this is the qubit 0 and this is qubit 1. If you have more tensor product, index increases. And same for when you abbreviate or omit this tensor product symbol O plus here. Still, this is for the qubit 0. So it means that the material that has a quantum information which is indexed by 0 has cat 0 state. It has an information which is represented as cat 0. And same for the cat qubit 1. And also we can not only just omit this tensor product symbol, we can just combine these two digits and write 0, 0. So this is perfectly valid because we know what we are talking about. And even further, I can abbreviate it as 0. Because, so basically, this number is going to be list or sequence of zeros and 1. It's going to be binary representation of some digit, some number, integer, positive or 0 integer. So I can just abbreviate it as an integer here. So same way, I can rewrite 0, 1 as 1. Well, that's obvious for now, but for 1, 0, I can write 2, and 1, 1, I can write 3. So it's very, it's a clean way of writing down the quantum state. You don't have to write the tensor product many times. So when you have n-qubit state, so you have cat 0 to cat 2 to the n minus 1 state up so far. So this number 0, 1, 2, 3 are actually the index of the matrix here where the 1 is located. So we usually call this row as a first row, which means that we put index as 1, 2, 3, 4. But for now, let's just shift the index here. So this is the index 0, 1, 2, 3. Okay, 0, 1, 2, 3. So you can see that the place where you have 1 here perfectly matches to the number we have here in the representation. So this is the commonly used notation for the tensor product. All right. Okay, so let me give another example here. So let's try to compute the following bracket. Operation using matrix. So first of all, I want to take the bracket of psi 1 and psi 0, where psi 1 cat is, psi 0 cat first. 0 cat is 1 over square root of 3, 0, and this, and psi 1 is this. Let me give another one. I also want to make psi 0, psi 1, where psi 0 is now 3-qubit state, 0, 0, 1. And psi 1 is 1, 0, 0, 1, 0, 1, 1, 1, 1. So now you know what I'm talking about here. So in the 3-qubit state, I omit all the tensor product notations and I just listed zeros and ones. I could just abbreviate even further to a number. For example, this one is 4 and this one is 5, but I think this is better to understand what's going on when you take the computation like this. So I'll give it some time to find the answer for 1 and 2, and then we can do it together. So if you, after you've done the computation using matrices, compare your answer with the usual computation using the bras and cat. Okay, for these two, we can do both of them. So let's look at the first one. So I need to take psi 1 bracket with psi 0. So I need to take the bra of psi 1. So what is the bra of psi 1? So the first one, I have bra of psi 1. As a conjugate, I take the conjugate of all the coefficients here, minus I square root of 6, 0, plus square root of 5, square root of 6. And then I take matrix representation of this bra, which is minus I over square root of 6, minus 5 over square root of 6. I'm sorry. So 1 by 2. And then multiply with the matrix representation of psi 0 ket. So it's going to be minus I over square root of 6 square root of 5 over square root of 6 times, what's the representation? It's 1 over square root of 3 and minus I square root of 2 divided by square root of 3. And it's going to be, let's say, minus I 3 over 2 minus 2, 3. 3 minus I over square, no, actually, 3 square root of 5 over 3, right? So that's the inner product. And you can do that inner product in the, not using the matrix, just using the bracket operations that we know of. So how do we do that? So first I take bra size 0, and then it's so okay. So same way we introduce the bracket operation, but let's use the 1 bar here. So this is the bracket here. So how do you compute this? First, you just psi 0 here. I think I made a mistake here. So it's bra 0. Sorry, it's a bra 0. Okay, so put minus I square root of 6, 0 plus square root of 5, square root of 6, 1. And then, so this is the psi 0 bra. And then what's the psi 1? I made a mistake here. So I think I should take the bra of psi 1, right? Okay, so let's fix it. So anyway, so what I computed is the psi 0 psi 1, right? Yes. So it's going to be psi 0 psi 1 of conjugate. So whenever you have an inner bracket operation, when you switch the order, you have conjugate. That's one of the conditions we have inner product. in the complex vector space. I mentioned in the previous class. So we found this already for this psi 0 bracket with psi 1. So we only need to take the conjugate of this complex number. So it's going to be I over 3 over 2 plus I square root of 5 over 3. Okay. All right, so let's do this way. And then, so psi 1 and 0. Let's see if we can get the same thing. So psi 1 bra is minus I over square root of 6, 0 bra, and plus square root of 5, square root of 6, 1, right? And what? No, I think I did computation correctly, right? I just made a mistake in the index. I just made a mistake in index here. This index is 1. Yeah, I did it correctly, right? Yeah, I did correct. Yeah, so the answer is just the same thing here. And let's say psi 0, I have and minus I square root of 2 square root of 3, 1. Okay. So what do we do next? We just distribute the bras and cat as if these are numbers. So when you take the bra cat with 0 and 0, it's 1. But when you take the bra 0 and cat 1, it's 0. So only thing that left is when you take the bracket of 0, 0 and 1, 1. So basically you get this times this minus I 3 over 2, and this times this minus I square root of 5 over 3. And that's it, right? We get the same thing. And how do you do the second one? Of course, you can make it into 8-by-1 matrix, right? Because, I mean, that's the way we have to do it. Because so we have psi 0 given as these. So it means that so this is number 1. So this is 1. Sorry, 0. Sorry, it's a 1, 1. Yes, when I'm talking. So yeah, and then this is 5, right? And how about this? 7. Right? So when you write 8-by-1 matrix, there are 3 places where you have non-zero entry. On the first, so including the 0, 0 is the first entry here. So the with the index 1, which is the second row, you have entry 1 over square root of 7. And on the fifth, which is the 6th row of the matrix, you have entry this. And on the 7th index, which is the last entry of the last row, you have this entry in your matrix. So and then you take the conjugate transpose, because this is the bra, and then multiply with another 8-by-1 matrix, psi 1, given by this information. But, well, let's do it different way. I already gave you the process of doing the matrix computation, and it's not going to be fun write down all the 1-by-8 matrix and 8-by-1 matrix. So let's do it this way. So if you look at this 3-qubit state, there is only the certain base states are inner product and survives. So for example, what happens when I inner product with inner product 0, 0, 1 state with 1, 0, 0 state. What's the inner product here? So when I take a bra of 0, 0, 1, so it's 1, 0, 0, and then I take the inner product or bracket with 1, 0, 0. What is it? Is it 1? So I think, so it's just a notation problem, but I mentioned that so it's a bit tricky to say this way, but when you take the bra, I said I switched the order of the tensor product between bras. So this is the bra of the cat 001, which is on the first summand in the size 0 cat. And so this is basically 100 is 1 bra, 0 bra, and 0 bra. Okay, so when you take the inner product like this, you have to take bras in this order and then multiply with the bras of cat. 1, 0, 0. And then what happens is you combine the bracket from the inner to outer direction. So first you take the inner parts, which are immediate subsequent to each other. So we have bra 0 and cat 1. When you combine these two, you get the bra 0, 1. So it's 0. All right? So it's already 0, so you don't have to carry out anymore. So the inner product is always 0. So it means that if I take the bracket between these two cat states, 0, 0, 1 and 1, 0, 0, you get 0. So when do you get non-zero? When do you get 1? Well, let's say, well, maybe it's because I don't have any common in every digit of these 3 digits. That's why maybe I get the 0. How about I take the inner product between 1, 0, 1 cat and 1, 0, 0 cat? Let's try that. So if I take bra of 1, 0, 0, 1, 0, 1, and then the second psi 1 is cat of 1, 0, 0. So you first take the inner product between bracket of 1, 1, and then you take the bracket of 0, 0, and then at the end, you take the bracket of 1, 0. So what's it gonna be? So first, it's 1, yes, not 0. And second, you get 1. But the end, you get bracket of 1 and 0. So eventually, it's going to be 0. So it's 1, 0 times 0, 0 times 1 and 1. So if I just name it here, so this is the first bracket, second bracket, and third bracket. So this is coming from the first bracket, second bracket, and third bracket. So these, each of inner product is an inner product between the two quantum states in the same qubit. So you look at the bracket 1, 1 here. So this, maybe I should take the last one here. So look at the bracket of 3 here. So where does 0 come from? It's the quantum state on the qubit 0. And where does bra 1 come from? It was the bra of the cat 1, which is the quantum state of qubit 0. So this is the bracket of quantum state bracket between, well, let's say, on qubit 0. And same thing here, it's a qubit 1. And same thing here, it's bracket on qubit 2. Okay, so when you take the bracket operation in between two n-qubit state, you're taking inner product or bracket operation on each qubit state in each qubit, and then if one of them it becomes 0, then everything goes to 0. Because whenever you have an inner product 0, it means there's nothing there. If one of the qubit has nothing, then all the other qubits have no information. So what do you do when you need to compute this? So you need to just match the same qubit, same cat state here. So this is our only way you get the non-zero entry. So when you combine the bracket of this cat and this cat, you get non-zero. This cat and this cat get non-zero. So you have to carry out the computation in the following way. So the bra size 0 is here, so you have to take the conjugate of coefficient of size 0. It's I over square root of 7, not minus I over square root of 7, times here, this one, I 2 over 2, and the same thing here, minus square root of 5 over square root of 7, and times I over square root of 2. So well, you can make it simpler if you want to. That makes sense? So sometimes if you want to implement the quantum computer as a simulator in classical computer, it's a good idea, it's a better idea to use the bracket operation as it is in a symbolic way, because if you want to make everything in the matrix, let's say you have 1,000 qubits and you want to implement into the classical computer as a matrix, then it means that you have to have 2 to the power of 1,000 times one matrix. At least your array should be as long as 2 to the 1,000 power. How big it is? It's too big, right? So it's very inefficient, because most of the entries in that 2 to the power of 1,000 array will be 0, and only a few of them will be non-zero. So in that case, you can just store the information where you have non-zero entries and what are the quantum states which has a non-zero coefficient, and then carry out the computation with those entries. All right. So any other question? If you don't have questions, I want to move on to the next topic here. Let's talk about the measurement. So measurement is the key process whenever you do the quantum computation. If you don't measure, nothing happens. Nothing meaningful thing comes out from any of the quantum algorithms. So what is the measurement? It's just observation. It's just the Schrodinger's cat story. So a quantum measurement is collapsing a 1 qubit state into a base state by observing via orthogonal basis. So if you see any definition of quantum measurement, they're all different. The Wikipedia defines it one way. The paper or book defines it the other way. It's not really precise as a mathematical definition, but what I could just do, I mean, I can make it into a mathematical definition too. but there are also some terminology involved in the quantum measurement. You can see that I used the collapsing and I used the word observing here. And also there are some mathematical terminology called orthogonal basis and so on. So I don't want to make it a too mathematical and or I don't want to make it a too physicist way of doing it. So what is it? Basically, when you observe quantum state, it's like a Schrodinger's cat. When you observe it, it is spotted in one certain state. Like either cat is dead or alive, right? When you observe it, but you don't know whether it's dead or alive. Basically, it's actually the dead and alive state are coexist in the same situation, but you never know which one is it. When you spot it, when you spot the ion or the electron, you can observe it where it is, but before you observe it, it is everywhere, literally everywhere. It's not moving it. It's not moving in a certain time in a certain position. It's actually everywhere. But when you spot it, you can see where that is. So, so therefore, it's the collapsing of the state. And once you observe it, now it's fixed. Of course, for short, only for a short amount of time. It's collapsing, and so it's fixed. And then doing that measurement is sometimes called observing. And when you observe, you always need to apply certain bases. Without basis, you don't know whether it's up or down, left or right. You have to have certain standard basis that you're observing it. So when the measurement always comes with this rule, the important rule, most important rule in the quantum mechanics and quantum computer. So it's called the Born's rule. So, and also important notion is that it's about the observing one qubit state. So you can observe n qubit state, but this observation is done independently. So it's going to confuse when I introduce the entanglement a bit later, but basically the observation is only done in qubit base, and you cannot observe two qubits at the same time. It's impossible. You're just doing one by one. Okay. So Born's rule is about observing one qubit state, and suppose that psi 0 and psi 1 is an ortho normal basis of H1, the set of all one qubit state. For example, you can set 0 and 1. So here, I used orthogonal here, but I mentioned that it's orthonormal, which means that each quantum state has an inner product or size equals to 1. When you take the inner product of itself, it becomes 1. But when you take the measurement, in principle, you don't have to have orthonormal basis, but here, we're going to assume that every basis is actually orthonormal here. So anyway, you can assume that this psi 0 and psi 1 is a ket 0 and ket 1 if you want to. And then the probability to observe the state psi I, where I is either 0 or 1, by the measurement via that orthonormal basis, observing the quantum state on the quantum state or one qubit state psi, which has alpha 0 and alpha 1 as coefficient, is this. E psi I is alpha 0 square, alpha 1 square, alpha I square. So you have this probability. So you see that it's a real number because I took the absolute value of the coefficient. The coefficient is complex number. When you take the absolute value, it's always real. So you get the real probability. And if you combine the two probability observing psi 0 and psi 1, it's always 1. You do observe one of these, but the probability depends on the coefficient. So for example, let's say I have a psi state, which is 0 plus I, 1. What's the probability of observing 1 when I take the measurement? So the probability of observing 0, observing 0 is 1 plus 1, 1, right? And probability of observing 1 is, so 1, where does the 1 come from? It's I, let me write here. So it's I squared. Okay? And then same thing here. So it's 1 over 2, I squared. I squared. It's 1 over 2. So you have 50-50 chance to get 0 or 1 after taking a measurement with the basis 1 or 0 cat or 1 cat. So now you might wonder, okay, can we just always take the basis 0 cat and 1 cat instead of having this general state? Usually we can fix the orthonormal basis for measurement, but sometimes we have to take another basis to take another measurement. So let's try to do measurement with a different basis. So what are the other orthonormal bases other than 0 cat and 1 cat? So these two are also orthonormal bases. So I mentioned the plus cat and minus cat before, right? And why is it orthonormal? Well, let's say, let's try to compute the inner part, the bracket here. So, by the way, so let me remind you what that is. So it's plus cat and it's minus cat. So there's no complex number. So whenever you take the inner product, you don't have to worry about taking conjugate. So let's take a plus minus here. So it means that it's 1 over square root of 0 bra and 1 bra with 1 over 2 square root 2 and 0 minus 1, right? So there are 1 over square root of 2, so 1 over 2. And again, when you take the bracket here, just match the same bracket here, 0, 0, and 1, 1. So there are 2, so it's 1 plus 1, 2. So it's 1. Oh, sorry, so it's not 1. So the first one is 0, 1, or 0, 0, and the second one is 1, 1, but you have a minus sign here. So we have a 0 here. So plus cat and 0 cat is orthogonal because the inner product is 0. So orthogonal literally means that the inner product is 0. So geometrically, you can imagine that this has a orthogonal angle, but we are talking about the complex space. So it's really hard to say what the angle is in this case. So it is orthogonal. And also, let's try to compute the inner product of itself and see if it actually is normal vectors. Yes? No? Okay. 0 and 1 and square root of 2, 0 plus 1. Yeah. So and then you see 1 over 2 is here and 0, 0 bracket and 1, 1 bracket, 1 plus 1. is 2, so you get 1. So these are orthonormal bases other than 0 and 1. Now, let's try to express the same quantum state as the linear combination of plus ket and minus ket. And once we do, after taking measurement base with the basis of plus ket and minus ket, the probability will be dependent on the coefficient alpha plus and alpha minus. So if I say, okay, so alpha plus plus alpha minus over square root of 2, 0. So I'm expanding this second expression here in terms of 0 and 1 ket to find out what alpha plus and alpha minus is. And alpha plus minus alpha minus divided by square root of 2, 1. And it must be, so this must be 1, and this must be I or minus I? It's just I, right? Okay, so alpha plus plus alpha minus is square root of 2. Alpha plus minus alpha minus is square root of 2i. So therefore, I have alpha plus to be 1 over 2 square root of 2, 1 plus I. And alpha minus to be square root of 2 over 2 I minus 1. Okay? So what's the probability of observing plus state after taking measurement with the basis of plus ket and minus ket? So it's alpha plus square, alpha minus square, alpha plus square. So let's take the absolute value first. So what is the absolute value? It's actually easy to find the absolute value by looking at the complex plane instead of doing all the computation. So here, I can map this complex number into a point and the complex plane where the x-coordinate is 1 over square root of 2 and y-coordinate is also 1 over square root of 2. It's right on the x equals to y line. And what's the length from the origin here? If it's at the 1 over square root of 2, 1 over square root of 2, it has 45-degree angle. And what's the length between the origin? 1, yes. So it's on the circle, the unit circle. So what's the length of this line segment represent? It's the absolute value of the complex number. So I know that since it's on the unit circle, so size is 1. And same for here. So this is my alpha plus. And where is my alpha minus? It's right on the other side, alpha minus. Still on the unit circle, its size is 1. So I know that this is 1, this is 1, this is 1. So therefore, it's 1 over 2. And same thing for observing minus 1. Probability of observing minus 1 is also 1 over 2. Okay, so here's an important assumption. In entire quantum computing business, we're not going to assume that this denominator is other than 0. So here, we mark the alpha 0 square, beta alpha 1 square of 1 qubit state, alpha 0, 0, and alpha 1, 1 is called the strength of psi. So maybe the strength has a meaning in physics, but in quantum computer, I said everything is just end with the measurement. And when you take the measurement, it's always relativistic. So it really doesn't matter whether you normalize the original quantum state into a strength 1. So we always assume that the strengths of the quantum state are 1. Okay, we always assume that. So whenever you want to make a quantum state, you have to make sure that the coefficients in your base state are sum to 1, square sum to 1. So here, let's look at this exercise here. All right. So here we have so this assumption applies not only to 1 qubit state, it also applies to n qubit states. Let's see this one. Square root of 3, 0, 1 plus I square root of 3, 1, 0, and 1 over square root of 3, 1, 1. Just think about naively. So after taking measurement on both of the qubits, so there are 2 qubits, qubit 0 and qubit 1, you can only observe 0, 1, 1, 0, or 1, 1. Because these are the only states we have in the quantum state. But when you take the observation, you have to collapse this quantum state into one of these. So just think about naively, what would be the probability of observation on these 2 qubit states? So what is the probability of observing 0, 1? Yeah, 1 over 3. Why?
Because the total probability is 1, and the probability of 0 1 state is 1/3.
Yeah, yeah. So you take the square absolute value square, and 1/3, and the square sum in the absolute value square sum of all the coefficients are add up to 1. So the total probability is 1. So what I mean by that the strength is normalized to 1 is that if you take all the square sum of this absolute value, then you get 1. Okay. So you can say that, okay, so when I take the measurement on these 2 qubits, so you get the 33% chances of observing 0, 1, 1, 0, and 1, 1. Now, there's a tricky part. Okay, so if you have just take a measurement on 1 qubit, let's say qubit 0, or qubit 1, let's say. Qubit 1 is easier. So let's say when you do that, what is the probability of observing 1 after taking measurement on qubit 1? So via 0, 1 basis. So after this point, we're going to always fix the basis to be 0 and 1, otherwise stated. So let's say I just take the qubit 1 measurement. I didn't do anything on the qubit 0. I just take the qubit 1 and measured it. What's the probability of observing 1? What do you think? So naively thinking, if you take the measurement on both of the qubit, there are only one case, as the probabilities are same, there are only one case that you observe 0 on the qubit 1. There are two cases that you observe 1 on the qubit 1. So remember that qubit 0 is the rightmost part, and the qubit 1 is the leftmost part here, 0, 1, okay? So when you just concentrate on the qubit 1, then 2 out of 3 gives you 1, right? So this one, this one, and this one. So what would be the probability then? Yeah, 2 out of 3, right? So let's make a computation, not by using in our intuition. Let's make a computation. So psi can be written as follows. So we have 1, 3, 0, tensor 1. And then let's make it clear. So we have 1 tensor. So let's put all the coefficients inside for now. 0 plus or minus 1 over square root of 1. Okay. And then I want to normalize these two. I want to normalize this 1 qubit state, because this is about the qubit 0. Okay? So when I normalize, what do? I first take the strength of this 1 qubit state and divide out by the strength. So this strength, what is it? 1 over 3 plus 1 over 3. It's 2 over 3. Okay, so it's just square root of 2 over 3, right? Or I mentioned the square. Okay, so let's take this way. So now I have to take the square root of 2 over 3 and then divide it out with this, and then make it the same quantum state. So I need some coefficient over here. So anyway, so this one cat state on the qubit 0 is already normalized because it has strength 1. So I don't have to do anything on here. So this part is okay. And then here I need to take 2 over 3, 1, tensor product with, okay, so here I over 3 over 2 over 3, because I have to divide out with the square root of strength so that this whole strength becomes 1. And 0 minus 1 square root of 3 divided by 2 over 3, 1. So now I have the qubit 1 qubit state on the qubit 0 is normalized to 1. And because of that, I have new coefficient on the qubit 1 of this tensor product. Now, I said the observation is independent to qubits. It can be done independently on each qubit. So this way, so we have the tensor product, linear combination of tensor product of the qubit state, where the qubit zeros are always normalized to its strength 1. So when I take the measurement on the qubit 1, I only take what is the possible state of my quantum qubit 1. So in the first stage, if I have a 0 cat, what is the 0 cat? The chances of observing 0 cat here. So it has 1 over square root of 3. So it's already normalized. When you take the coefficient of 1 over square root of 3 and square root of 2 over 3, there are some square is 1, so it's already normalized. The chances of observing 0 cat for the qubit 1 is 1/3, and the chance of observing qubit cat 1 is 2/3. So that's why we get the 2/3 probability to observe 1 here. The same way, there are 1/3 of a probability to observe 0. So we're gonna wrap up this class with a small remark. So now, what happens to the qubit 0 after I take the measurement on qubit 1? So let's suppose that I observed qubit 1. I observed 1 for after measuring the qubit 1. It means that it collapses to the cat 1 state, and there's no cat 0 state anymore. That means this vanishes after taking a measurement. And this also fixed to the 1, just fixed to 1. Okay? So I changed the quantum state by taking a measurement. But then instantly, the quantum state of qubit 0 is also changed. Before, we had the possibility of having cat 1, but after taking measurement on qubit 1, which is physically apart from the qubit 0, the qubit 0 state has changed to this quantum state. So it's not surprised right now, but if you look at the quantum entanglement, the entangled state, it's quite surprised. It's very not intuitive. So we're going to talk about quantum entanglement next time and see what kind of paradox or weird thing going on if you think about what's happening in the measurement on the entangled state. So if you have any questions, let me know after class, or we can see on Wednesday.